Okay, so 6.2 is approximating areas with Riemann sums. The graph of a function g of x is shown to the right. Approximate the area under the curve on the interval 2 to 6 within subintervals by using a left rectangular approximation method. So important here is that we're only approximating the area. We are not getting the exact area. Okay. We are on the interval 2 to 6, and it doesn't give us a specific number of subintervals. So instead, what we're doing is we get to choose how many intervals we're using. And then lastly, we're using a left rectangular approximation method. So the idea behind this is it's a lot easier to find the area of a rectangle than it is to find the area of a not common shape. So here I'm first going to highlight my interval from 2 to 6 to show that this is the area that I'm trying to find. And since it wants me to do a left rectangle, all that means is I'm going to be making sure that the left side of my rectangle is the side that touches the curve. Okay. So in order to determine how many rectangles we're going to use, we have to first know what happens when we increase our n subintervals. So if I just start with 1, so like n is equal to 1, I can find a width, which is us taking the interval 2 to 6, subtracting those values, so 6 minus 2 is 4, and that gives me the width. Okay, what this means is that I would use one triangle with a width of 4 to estimate this. Okay. Well, let's say instead of using one triangle, rectangle, one rectangle, I want to use 2 rectangles. Okay, the width is still going to be us subtracting those 2 numbers, but now we're going to divide by n. So this is going to be 4 divided by 2, which is 2. So this gave me 2 rectangles width of 2. Okay. We could keep going up to infinity if we wanted to. Okay. For the sake of this, since we are graphing, I'm just going to stop at n equals 8. So if I continue that process, I still have the width that's going to be 4 on the numerator. But now I'm dividing by what? 8. So now my width becomes 1/2, which means I'm going to create 8 rectangles with a width of half. Okay. As our n value is increasing, what is happening to the width? It's decreasing. So we're able to fit more rectangles into that space. So the idea behind this, and I'm going to write this off to the side, is that the more rectangles equals a better approximation. Meaning if I was to use only one subinterval, n equals 1, and get an area from that, it would not be as accurate if I was to use n equals 8 and create 8 rectangles and find those areas. Another way to think of this is as the number of rectangles approaches infinity, the approximation is going to approach the actual area. So more rectangles we have, the better our approximation is to getting closer to the actual area. Okay. So if I was to draw those 8 rectangles on here, since it's a width of half, I know that I am going to have rectangles that are splitting up each of these half marks here. So not only is it going from 2, 3, 4, 5, 6. It's also going 2.5, 3.5, 4.5, etc. Okay. I also know that only the left side of the rectangle is going to touch the graph. So I'm going to make sure that only the left, let me change the color here, is going to touch. So I'm putting these points on the halves and on the whole numbers. Okay. So when I'm drawing my rectangles, and only the left part is going to touch, I'm going to have these little rectangles. Oops. So that's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so everything that I shaded in with those rectangles is my area approximation. Notice it's not covering exactly all of the pink highlighter. Very close, but it's not covering all of it. So I can't say this is going to be the exact area. Okay. So what we just did, this method, is called the Riemann sum. Okay. And it was named after a German mathematician who discovered it. So in this first example, it's just showing you the concept. Okay, any questions so far? Yes?
So, like the left side, that means like the left side of the first rectangle that you draw has to be touching the,
Yes.
line of it.
Yes. It will make more sense when we look at all the different types, the left, the right, and the middle. Okay. So for this next example, it gives us a function, and then it tells us to find all the different Riemann sums. So we kind of looked at what it means to be left Riemann sum, and now we're going to look at right Riemann sum. The other two graphs that follow on the next page are also part of this example. So we're going to look at 4 different ways. So starting with left Riemann sum. Left Riemann sum means that the left corner of our rectangle touches the curve. Versus right Riemann sum means which side is touching the curve? The right corner. So in these examples, they give us the interval 2 to 8. So what I'm going to do first is I'm going to make sure I highlight that interval of what the actual area would be. And I'm going to do that on both graphs. Okay, so this is ideally the actual area, what we're trying to achieve. Another important thing to mention is that instead of saying nth subintervals, they actually tell us how many to create. And they say that we're creating 3 subintervals. So since we're creating 3 subintervals, then we're saying that our n value is equal to 3. Okay, which means our width, bless you, is going to be our interval where we subtract those 2 numbers, so 8 minus 2. And then we're going to divide it by 3 because that's our n value. So it's going to be 6 over 3, which is 2. So we have an n value of 3 and a width of 2. And since the right Riemann sum is using the same interval, we don't have to rewrite that. We can just say, okay, it's going to be the same as the left Riemann sum. N equals 3, width equals 2. That means we're going to have 3 rectangles with a width of 2. Okay. So for the left Riemann sum, remember only the left side of the rectangle is going to touch, which means we're going to look at the left side of the interval first, which starts at 2. So we're going to use 2, and then since it's a width of 2, we're going to go to 4, and then we're going to go to 6. Okay, the reason why we stop at 8 is that rectangle would end up going past that curve, so we don't need to include that. Okay, once we have those values, those are the points that are going to be on our curve. Okay, and only the left side is going to touch. And we have a width of 2, so I am going to, from the left going to the right, do a width of 2 units on each side, and then I'm going to bring them down to form my 3 rectangles. So again, notice if we were to continue and use 8, that would be completely off the graph. So what we're going to do is we are going to take these 3 rectangles and approximate the area. So everything that I'm kind of highlighting red there is the approximate area. Notice that we didn't cover all of the yellow, so all of the exact area, and we also went outside of the function. Okay. Which means when we calculate this, would this area approximation be too big or too small? Too big. Okay, and we're going to see that when we calculate it. Well, in order to calculate this, we know the area of a rectangle is base times height. So when we find this, we're going to end up using the equation that they gave us above. So area is equal to 2 times f of 2, because we used 2 on the x-axis. So in order to find what that height is, we're going to plug it back into the function, or we could look at the graph. Plus 2 times f of 4 plus 2 times f of 6. Okay, so we're taking the area of each of those rectangles and adding them together. Okay. When we do this, we get 2 times 6, that's f of 2, plus 2 times 8, plus 2 times 6, which is 12, plus 16, plus 12, which means that our area is approximately 40 units squared. 40 units squared. And again, we're making the assumption that based off just our diagram, we're going past the graph, okay, that this is going to be too big. Okay, so using a left Riemann sum on this, we're making the assumption that this approximate for the area is too big. So what would be our guesses for using a right Riemann sum? Our approximation is probably going to be too small. Any questions on the left? Yes.
When it says like f of 2, f of 4, f of 6, where do we get those values from? Like the 6 and the 8 and the 6?
You could either look at the graphs. So for example, f of 2 is at 6.
Oh, yeah.
F of 4 is at 8. And f of 6 is at 6. Or you could go back up here. The equation's here. You could plug it in.
Okay.
Okay, so on the right Riemann sum, that means the right corner is going to touch the curve. So instead of looking at the left side of the interval, we're now going to look at the right side of the interval, which means we are going to include 8 this time. Okay, and since this is still a width of 2, I'm also going to choose 6, and I'm going to choose 4. Okay, notice I'm only choosing 3 because we only need to find 3 sub-intervals. I don't need to continue and then choose 2 and then 0. Okay, so then from those values, I'm going to plot those points on the curve. Notice that 8 is right there on the x-axis. Okay. And then we have 6 and then 4 up there on that curve. Okay. Since this is a right Riemann sum, only the right corner of the rectangle is going to touch, and we're still doing a width of 2. But notice down here at the 8, in order for me to do a width of 2, I'm going 2 units on the x-axis. And I'm not able to put any height here. So what do you think f of 8 is going to end up being? 0. Okay, this one, I can do 2 units. And then this one, 2 units. Okay, and again, the direction where we're doing our units depends if it's a left or right Riemann sum. Okay, so then I can just bring them down. Okay, and then here I'm only looking at this area. So again, we made the assumption that this is probably going to be too small, and we can see it here in the diagram because there is a lot of yellow space that is not being covered. Okay. And we would find the area the same way. So we have the area is equal to 2 times f of 4 plus 2 times f of 6 plus 2 times f of 8, which is going to be 2 times 8 plus 2 times 6 plus 2 times 0, which is 16 plus 12 plus 0. So this gives us an area approximation of 28 units squared, which we said was too small. So based off of these 2 Riemann sums, the left and the right, we know that the left one was too big, the right one was too small, so our area has to be somewhere in the middle, somewhere in the middle. So we know our area is going to be between 28 and 40. That's as much as we can say here without actually finding the exact area, which again, we won't learn how to do that until notes 4 when we talk about integration. Okay, so this was the first 2. Any questions about these ones? Okay. Okay, so remember, we're still on the same example, so we're still using the same interval, the same 3 subintervals, and now we're just talking about 2 different types of sums. So we have the midpoint Riemann sum. Any guesses what that means? The middle is going to be touching the curve. So the middle of the rectangle touches the curve. And then the other one is trapezoidal sum. So instead of using rectangles now, we're going to be using trapezoids. And we know from yesterday that that is the area for a trapezoid is area is equal to 1/2 h times base 1 plus base 2. If we were to choose out of all 4 of these sums, these 2 would be the most accurate. So I'm going to write that off to the side. These are more accurate than left/right sum. And you'll notice when we solve these that we're still going to get values that are a little too big and a little too small. We're still going to end up with that interval, but our interval is going to be a little better with these 2 versus the last 2. Okay. If I had to pick out of all 4 of these, trapezoidal is going to be the best one. The reason for that is when we draw a trapezoid, when we do the diagonal, it's going to follow the curve a little better. So we're going to end up getting more of the area and less of the empty space that we don't need. Okay, so for midpoint Riemann sum, we still have that n is equal to 3 and our width is equal to 2. Okay, the same information that we used on the last 2. And I'm going to say over here that this is also going to be the same. But instead of using the word width, we're just going to use the word height. That way we can use that formula for area of a trapezoid and not get confused of where we're plugging in width. Okay, this just tells us that where we see width, it's going to be height. Okay, so since the midpoint one is using the middle points, first I'm going to just shade from 2 to 8, like I did on both of the previous 2. So now if I'm looking at the interval 2 to 8, I need to pick the middle numbers. And so in this case would be 3, 5, and 7. Okay, all those middle numbers. And those numbers are going to be where I plot the points on the curve. Okay. And since this is going to be a rectangle that has a point right in the center and my width is 2, I'm going to make sure to go out 1 unit on either end. And then draw my rectangles. Okay, so notice this one had pretty good coverage. Okay, it's not too far outside of the curve, and it almost has covered majority of the yellow. Okay, but again, it's still going to be an approximation. So we're still doing area of a rectangle, so this is going to be area is equal to 2 times f of 3. Plus 2 times f of 5 plus 2 times f of 7. Okay. This would be one where I would use the formula because if you notice some of my points are not exactly or exact points on that y-axis. So if you were to plug them in, this would be 2 times 7.5 plus 2 times 7.5 plus 2 times 3.5, which is 15 plus 15 plus 7, which gives us an area approximation of 37 units squared. Yes.
When you choose like the numbers like 3, 5, and 7 for the x, does it matter? Like if we were to do this again and we chose 2, 4, and 6, would that like change our answer?
Yes, because 2, 4, and 6, 2 is including a endpoint in our interval. So when you include 2, it's under the assumption that you're doing a left Riemann sum, not a middle. And so the reason I picked 3, 5, and 7 is because if we look at all the numbers in our interval, we have, let's say, 2 to 4, the middle number would be 3. 4 to 6, the middle number is 5. So it's based off the interval. For midpoint, we don't use any of the endpoints. So we wouldn't use 2 and we wouldn't use 8. Okay, so for this next one, again, it wants 3 sub-intervals, so we're going to create 3 trapezoids. So since we have a width, or in this case, height of 2, I'm going to start at 2, because that's in my interval, the very beginning. This is where it differs from the other ones. Okay, and I'm going to do my point at 2. Okay, then the width or height is 2, so I'm going to go from 2 to 4. And then from 4 to 6, and then from 6 to 8. Okay, so for the trapezoidal, we're using all the points, including the endpoints, and the numbers we choose is based off of the height, which in our case was 2. Now instead of creating rectangles, we're going to take those points that we plotted and we're going to do a diagonal between them. Okay, and then I have a diagonal. Make that a little better here, and then a diagonal here. Okay, and then I just bring those lines down from my points. So here, I now have 3 trapezoids. That you notice none of them are going over the function. Okay, and we almost have everything covered because of those diagonals being able to follow the curve a little better than our straight-lined rectangles. Okay, so in order to find this area, we're going to use the formula for area of a trapezoid. So I have area is equal to 1/2. Our height is 2. And when we're talking about our bases, we're going to see what 2 points connected. So we started with 2, and then we connected it to 4. So this is going to be f of 2 plus f of 4. Okay. Plus 1/2 times 2, and then we're going to look at the next part that we connected, which was 4 to 6. So this is f of 4 plus f of 6 plus 1/2. So we did our first 2 trapezoids. We have that last one times 2 times f of 6 plus f of 8, the last 2 points that we connected. You would plug it in to find those values, and we end up getting 14 plus 14 plus 6, which means our area approximation is 34 units squared. So again, if we look at these two diagrams, we see that the midpoint Riemann sum was a little bit too big, and then the trapezoidal sum was a little bit too small. Okay, so I would say too big, too small, which means a better approximation for our area is that our area will be between 34 and 37. Okay. Remember, we were using the same exact data in the last 2 Riemann sums, the left and the right. That interval, when we did left and right Riemann sum, was from 28 to 40, a larger interval than the midpoint and trapezoidal, where we got it to shrink down to 34 to 37. Okay, that's why they say these 2 summations are the best for approximating the exact area. Any questions so far? Yes?
So why can't we average the left and right Riemann sum to get the area? Because I feel like that makes sense to me, to average those 2 numbers.
I mean, you would get probably a little closer, but it wouldn't be exact. Because even if you say you combine this, I still feel like there would be a lot of unnecessary area outside of the function, and potentially there could be very small parts of the area under the curve that wasn't covered that maybe we just don't see when we graph it. Mm-hmm. Don't worry, we're going to learn about integration. You're going to find the exact values. Okay, so now we're going to talk about how do we know if it's an overestimate or an underestimate. So if we have a function that is increasing, if we're looking at a left Riemann sum, then that is going to be an underestimate. And then a right Riemann sum will be an overestimate. Okay. And again, this is for an increasing function. Because let's say we're trying to find this total area here, and they don't give us an interval, so we're just going to assume it's this entire area here. And they also don't give us an in-value talking about any of the subintervals, so I'm just going to go by each of them with a width of 1. So left Riemann sum, again, we are making sure the rectangle touches from the left. So when I draw these rectangles, I would make sure that only the left side of the rectangle is touching. And when I do that, you'll notice that this is an underestimate because it is not covering the entire area, and it's not also going over it either. Versus a right Riemann sum, okay, where the rectangle has to touch from the right. Notice how on this increasing function, we are using area that is not part of the function. Okay. For decreasing functions, it's going to be the opposite. So left Riemann is going to be an overestimate, and right Riemann is going to be an underestimate. Okay, and again, if we were to show this, again, we don't know the interval, so I'm just going to highlight this entire part, create my rectangles with a width of 1. So left, I need to make sure that the left side touches. Okay, and again, you see that it's an overestimate because it goes above the function. And then right Riemann, we need to make sure that the right side touches. And then you see here that this doesn't fully cover the entire yellow shaded area, but it also doesn't go over it, so it's an underestimate. Okay. So for left and right Riemann sum, you just have to know if the function is increasing or decreasing. Okay. For midpoint summation and trapezoidal summation, instead of looking at increasing or decreasing, you're going to have to know the concavity. Okay. So first I'm going to shade all of this. Okay, so in this one it's talking about the trapezoid estimation. And so when we have concavity, if it's concave up, then using the trapezoid method is going to give us a over approximation or an overestimate versus concave down, which is going to be an underestimate. And we see that on this first graph by how the trapezoid part of the function is going to go a little over the graph. So remember, once I have those points, I'm connecting them. And for this one, it looks like it doesn't go over a whole lot, but it's still over. So I would make that emphasis on your notes that you do see that the line goes a little over. Versus an under, where it is not going to go above that function, but stay completely under that curve. Okay, and of course I could have continued making more on either side to cover more of that yellow area, but I just stuck with 3, just for the example. It doesn't give us the example of midpoint summation. All you need to know is that for midpoint summation, it's going to be the opposite of trapezoid. Which means if we were doing a midpoint summation and we had concave up, would it be an over or under estimation? Under. And for concave down, it would be over. Okay, any questions on over and under estimation? The last part of the notes is showing us how to use Riemann's sum with a table of values. Okay. This is what majority of your homework is going to look like using the table of values. You will have a couple graphs, but majority it will be tables. So it says the rate at which water is being pumped into a tank is given by a continuous and increasing function R of t. Very important information. That's why I'm highlighting it. A table of selected values of R of t for the time interval t between 0 and 12 minutes is given below. Okay, so we have a table here where time is in minutes and R of t is gallons per minute. Okay, in this table, we know that this is height and this is our base, or in other words, the top is x and the bottom is y. It says use the following Riemann sums with the given intervals to estimate the number of gallons of water pumped into the tank during the 12 minutes. So if we look at each of these sums, majority of them are telling us to do 4 subintervals. So what that means, if we were to actually draw those rectangles, we would have a rectangle here. So that would be one rectangle. Second one, third one, fourth one. And depending on which Riemann sum we're doing, left or right, is going to determine where we're looking and where we're starting on our interval. So for the right Riemann sum, we are going to start at the right side of the interval, which is going to be 12 minutes. Okay? And then we are going to go from 12 minutes to 9, 9 to 6, 6 to 3, and then 3 to 0 to represent all our intervals for height. When we do that, since it's a rectangle, we know we're going to do base times height. Okay? So that means since it's a right Riemann sum, we're only going to look at the right number. So if we're going from 12 to 9, that means we're going to multiply that by 27. Okay, 9 to 6, multiply that by 23. It's everything on the right of the interval. So what that looks like is that we have area is equal to 12 minus 9 times 27 plus 9 minus 6 times 23 plus 6 minus 3 times 18 plus 3 minus 0 times 13. Notice I am not including the 7 for gallons per minute into this equation because this is the right Riemann sum. I'm only using the right part of the interval. Okay, which means when I do the left Riemann sum, which number am I not going to use? 27. Okay. So for the right Riemann sum, we calculate this and we say that A is approximately 243 gallons. Okay. Since this is a right Riemann sum and our function is increasing, would this be an approximation that is greater or less than the true value? Greater. Because we know it's an overestimate. So we would say greater because R of t is increasing, and we know that from the problem. Okay. So again, using left Riemann sum with the 4 subintervals, we're just going to start on the left side of our interval. So this would be area is equal to 3 minus 0 times 7 plus 6 minus 3 times 13 plus 9 minus 6 times 18 plus 12 minus 9 times 23. And again, we did not include the 27 because that is all the way to the right of the interval. Okay. When we solve this, we get that area is approximately 183 gallons. And since this is a left Riemann sum with an increasing function, would our approximation be greater or less than?
Less than.
Less than. It's always opposite than the right. So we're going to say less, and again, the same reasoning is because R of t is increasing. Okay. Which means we couldn't use either the right or the left to estimate because the right is going to be too much. So 243 gallons, too much. The left is going to be too little, 183 gallons. We know the actual area is somewhere between that, but that's why we use these last 2 approximations to get a better idea of where that area could be. So for midpoint Riemann sum, it's telling us to use 2 subintervals. Since we're only using 2, so if we go back up here, it only wants us to take all this data, divide it into 2. So that means I would have to look at this as one interval, right, from 0 to 6. And then I'd have to look at this as another interval, okay, 6 to 12. Okay, within each of those intervals, I want to make sure that the midpoint touches the curve, and we know it's going to touch the curve on the y value. So I'm going to be using these middle terms, 13 and 23, because they're in the middle. And then I'm going to do that same process of the area. So this is going to be area is equal to 6 minus 0 times 13 plus 12 minus 6 times 23. You solve that out and we get that the area approximation is about 216 gallons. Okay, the last method of approximation is the trapezoidal. So we're going to be using the area of a trapezoid, which is area is equal to 1/2 h base 1 plus base 2. And since we're using those 4 intervals, we're going to be using the bases or the numbers that are next to each other. So if we look back at the table, that means we're going to be using 7 and 13. Those are the ones that are next to each other. Then we're going to use 13 and 18. Then what would be the next one? 18 and 23. And then the last one? 23 to 27. And that's what's going to consist of all 4 of our trapezoids. Okay. So writing that out, this is going to be area is equal to 1/2 times 7 plus 13 times 3 minus 0. That's the first trapezoid. Plus 1/2 times 13 plus 18 times 6 minus 3. Plus 1/2 18 plus 23 times 9 minus 6. Plus 1/2 times 23 plus 27 times 12 minus 9. So that's all 4 trapezoids. This is going to give us 30 plus 46.5 plus 61.5 plus 75, which gives us an area approximation of 213 gallons. So notice we went from our area being between 183 gallons to 243 gallons. And now we're between 213 gallons and 216 gallons. So this brought our interval even smaller and gave us a better approximation for the exact area. Okay. Why didn't they ask us the same questions they did in the first 2 about the approximation being greater or less than the true value? Because why? Sorry? Not quite. What do these need to determine if they're over or under? Concavity. Did the problem mention anything about concavity? No. So since it did not mention anything about concavity, we cannot see if it's an over or under approximation. So recall that we need concavity to see if it's over/under estimation. And again, since they didn't mention concavity, like they would have to mention it in the problem, this is concave up, this is concave down. We are not able to see how close these are, over or under estimation, to the problem. Based off of the other 2, I can assume that the trapezoidal is probably an underestimation, midpoint is probably an over an estimation, but we couldn't say that for sure.